Section 10.1 Interference of Waves and Light. You may have noticed the colors of reflected light in a thin layer of oil in a puddle, on a road, like the one shown in the figure in your notes. To understand why reflection from a layer of oil produces this colorful pattern, you need to understand the interference of light waves when they are reflected from or transmitted through a thin layer of material often called a thin film. When light rays traveling from air meet the upper surface of an oil layer, some of the light waves are reflected. Similar behavior occurs at the lower surface of the oil layer, with the result that light rays from both surfaces are reflected. These rays interfere either constructively or destructively, depending on their phase difference. For example, if the ray travels from one medium into a more optically dense medium, the reflected wave is inverted, so it will not constructively interfere. We know that a wave is inverted when it reflects from a fixed end or encounters a medium in which the speed of waves decreases. And this type of medium would be a more optically dense medium. Conversely, a wave is not inverted when it reflects from a free end or encounters a medium in which the speed of the wave increases. So if it were to encounter a less optically dense medium. Let's take a look at thin films and interference. Both surfaces of a thin film, this upper surface, which is the air-film interface, cause a reflection. Similarly, the second surface, which is the film, and the third medium interface, also causes a reflection. Now, when the index of refraction for these three layers, 1, 2, and 3, are increasingly more optically dense, 1, 2, and 3. So for example, if we're going from air to a film and glass, where the index of refraction for air is less than the index of refraction for film, and the index of refraction of the film is less than the index of refraction from glass, then we have two equations that govern when we will observe constructive interference and destructive interference. Now, destructive interference will occur whenever the path length difference for the light ray traveling through the soap film and back out is at a multiple of lambda over 2 in comparison to ray 1 that is reflected off the surface. So these values, where m is equal to 0, 1, 2, or 3, will correspond to areas of destructive interference. So in this situation, when the index of refraction of air, film, and glass are successively larger, one of the emerging waves will come out and cause a phase change. Now we have another situation in which, if you take a look, the index of refraction from air is less than the index of refraction from film, but now we've created another interface, so 1, 2, and the third is now less optically dense than the film itself. When this happens, then both of the waves will have a phase change, and the emerging result is a no phase change situation. So in this situation, all you need to know is that the equations flip. So we expect constructive interference to happen when 2t is equal to m plus 1/2 lambda over n film, And we get destructive interference when 2t is equal to n lambda over n film. And again, m corresponds to these whole number integers 0, 1, 2, and 3, which will allow for this pattern to occur. Let's take a look at a couple of examples to put this into practice. Sample problem number 1. Consider a soap film that is the thinnest film that will produce a bright blue light when illuminated with white light. The index of refraction of the soap film is 1.35, and the blue light is monochromatic with a wavelength of 411 nanometers. Let's collect all the information that we know. First of all, we have N air. The index of refraction from air is 1, which is less than the index of refraction for the film, which is 1.35, which is less than the index of refraction for glass, the third medium. This is 1, 2, and 3, which is 1.52. When this happens, we can look back at our equations. We are looking at the first set of equations, and we know that for constructive interference, we're governed by the equation 2t is equal to n lambda over n film. And for destructive interference, we are looking at 2t is equal to m plus 1/2 lambda over n film. In this example, they want us to calculate the thickness of the film if the soap covers a piece of crown glass with an index of refraction of 1.52. So we know that the wavelength is 411 nanometers, which is equivalent to 411 times 10 to the power of negative 9 meters, because nano means 10 to the power of negative 9, which corresponds to, in proper scientific notation, 4.11 times 10 to the power of negative 7 meters. Hopefully throughout this unit, you will come to understand the level of scientific notation required to express light in nanometers and in meters. Remember, nanometers are always 10 to the power of negative 9, and when converting those into meters, we're always looking at a power of approximately 10 to the power of negative 7 meters when we're dealing with visible light. So in part A, both reflections involve inverted phases, since the index of refraction increases from layer to layer. Therefore, we use the formula for constructive interference of the two waves when the phase change occur in both reflections. So we can use the equation for constructive interference, which states that 2t is equal to n lambda over n film. We can rearrange this. And remember that we're dealing with the wavelength of blue light here. So I'm going to put the little subscript blue to represent the wavelength for blue light. So T is equal to n lambda for blue light over 2 times the index of refraction for the film. We can plug in these values. The index of refraction for the first interface is 1. The wavelength of blue light is 4.11 times 10 to the power of negative 7 meters, divided by 2 times the index of refraction for the film, which is 1.35. If we punch this into our calculator, we end up with a thickness of 1.52 times 10 to the power of negative 7 meters. Therefore, the thickness of the film on the glass is 1.52 times 10 to the power of negative 7 meters. Now, suppose the reflections occur instead from a soap film on water with an index of refraction of 1.33. So we have air, excuse the sloppiness, air, soap, and now water. So we're looking at the situation where the index of refraction for air is less than the index of refraction for the film, but the index of refraction for the film is greater than the index of refraction for water, because we are looking at 1, 1.35, and 1.33. When this is the situation, we are governed by the opposite set of equations. So for constructive interference, we are looking at 2t is equal to m plus 1/2 lambda over n film. And for destructive, we are looking at 2t equals n lambda over n film. All right, so in this example, what we want to find is t. One ray is partially reflected from the upper surface and inverts because it's moving into a more optically dense medium. However, the second ray reflects from the bottom surface and does not change its phase because it's moving into a less optically dense medium. Therefore, we use the formula for constructive interference of the two waves in one phase change. So the equation that we're going to be using is this one right here, where 2t is equal to m plus 1/2 lambda over n film. Now, in order for this to be constructive, this has to occur at path lengths where 2t is equivalent to a path length difference from ray 1 of lambda over 2. And this happens when m is 0. If we put 0 in here, we'll see that we end up with lambda over 2. So we can add m equals 0, and we end up with, if we add a 0 in here, we have 0 plus 1/2 lambda over n film. I want to simplify this a little bit further. We have 2t is equal to 1/2 lambda over n film. I'm just going to erase this one. It's a little redundant. Now, when solving for t is equal to lambda over 4n film. So what I've done is I've brought this t down across the equal sign on the diagonal. So 2 times 2 equals 4. So we can calculate the thickness, subbing in these values. We know that the wavelength is 4.11 times 10 to the power of negative 7 meters. Again, we were dealing with blue light. Over 4 times the index of refraction for the film, which is 1.35. If we punch this in, we should get 7.61 times 10 to the power of negative 8 meters. All right, let's look at a third example. Making solar cells more efficient. In solar cells, incoming light passes through an anti-reflective coating to increase the efficiency of the cell. Suppose the index of refraction of the coating is 1.45 and the index of refraction from the material below is 3.50. In this case, you need to maximize the amount of transmitted light and minimize the amount of reflected light. Determine the thickness of the anti-reflective coating that will minimize the reflection of light and therefore result in destructive interference with a wavelength of 7 times 10 to the power of negative 7 meters. So we have air anti-reflective coating, which we shall call film, and then medium 2, we're dealing with 1.45, and the third medium, N2, has a much more optically dense index of refraction. So we know we're dealing with the first set of equations where we know from up above we have 2t for constructive interference is equal to n lambda over n film, and for destructive interference 2t is equal to m plus 1/2 lambda over n film. So in this example, the incident light ray moving from air into medium 1 will partially reflect at the upper surface. Since medium 1 is more optically dense than air, the light wave will be reflected and inverted at the upper surface. Similarly, at the lower surface of medium 1, a light wave will be reflected and inverted because medium 2 is more optically dense than medium 1. So to maximize the amount of light traveling through the coating, the two reflected rays from the upper and lower surface must undergo destructive interference. This means that the distance 2t that ray 2 must travel compared to ray 1 is equal to lambda over 2. Therefore, we use the formula for destructive interference when both waves change phase, which is the same as when both waves have no change of phase. So we'll set m equal to 0. For destructive interference, we know that it's m plus 1/2 lambda over n film. Putting in 0 for m, we get 0 equals 1/2 lambda over n film. Simplifying, we get lambda over 2 n film is equal to 2t, and t is equal to lambda over 4 n film. So we can sub these values in. We have a wavelength of 7 times 10 to the power of negative 7 meters over 4 times the index of refraction for the film is 1.45. Punch this into our calculator and we end up with 1.21 times 10 to the power of negative 7 meters. Therefore, the thickness of the anti-reflective coating is 1.21 times 10 to the power of negative 7 meters. Okay, we're going to move on to another concept called Newton's rings and air wedges. If you place a glass disc with a convex surface in contact with a flat glass surface, as shown in the diagram, and illuminate it with a beam of light, a phenomenon called Newton's rings occurs. Light reflects from both the upper surface of the flat glass and the lower surface of the curved glass. The light reflecting from the flat glass plate changes phase because of the air in between the two surfaces and has a lower index of refraction than the glass. However, the light reflecting from the lower surface of the curved glass does not change phase. The difference in phase length increases with the distance from the point of contact of the two glasses. Therefore, any monochromatic light with a wavelength of lambda will have a bright fringe at each location where the separation, which we'll call t, is half of a whole number multiple of lambda. So, 2 important points we need to remember. A, light reflects from both the upper surface of the flat glass and the lower surface of the curved glass. And B, Newton's rings are a series of concentric rings from light reflecting between the flat surface and the adjacent curved surface. So this is a very interesting phenomenon and actually produces a beautiful interference effect, but there are many practical applications of Newton's rings. A practical application of Newton's rings is checking lenses for imperfections. Spherical lenses, if properly shaped, will produce a perfectly spherical Newton's rings. Next, a similar phenomenon occurs with air wedges. To create a measurable pattern of destructive and constructive interference, researchers often use an air wedge, which is a wedge of air between 2 sheets of flat glass that have been angled to form a wedge. And I'll show you what that looks like. So here we have 2 sheets of glass, 1 and 2, and there's a wedge of air in between them. The upper glass is raised slightly, a very small distance, which we'll call T, and illuminated with monochromatic light. So why do we do this? Well, we can do this, number one, as a means to calculate the wavelength of light, but a more practical reason that we can see, especially in industry, is sometimes 2 sheets of glass will elicit this pattern of interference and indicate that there is a small object causing the separation of the layers in the glass. And we can actually use it to measure the length or the height of this object causing this separation. And our example will be one such example which shows the practical applications of the air wedge calculations. So we end up with this interference pattern with bright maxima and dark minima. The dark fringes occur whenever the separation distance of the 2 plates at a particular location is a multiple of 1 wavelength. To determine the first wavelength, or the first minimum rather, we have to set the path length to lambda over 2. And we know that when we have a path length of lambda over 2, that we get destructive interference. So our first minimum will occur, and we give it the symbol x1, and it'll occur at L lambda over 2t, where L is the length of the glass wedge, and t is the height of the air wedge, which we'll call T. To determine the next fringe, x2, we're going to set it at the second multiple of lambda over 2. So lambda over 2 plus 1/2 is lambda. So it'll occur at x2 equals L lambda over T. Now the separation distance between 2 fringes can be calculated as follows. We can subtract these two. Delta x is equal to x2 minus x1, and we end up with L lambda over 2t for an air wedge. So this becomes our equation. And we can do an example that shows the practical application of it. Sample problem number 1, interference effects in an air wedge. 2 glass plates are separated on one side by human hair. We have this human hair right here. And it's causing this air wedge between the 2 plates of glass. The light shining on the plates has a wavelength of 6 times 10 to the power of negative 7 meters. The light intensity is 0 at the point of contact of the two plates, followed by 9 alternating bright and dark fringes. So this entire length, which we'll call L is composed of 9 bright and dark fringes, each with a distance of delta x. That is the separation distance between the dark fringes. So we know from up above that our equation tells us that delta x is equal to L lambda over 2t. Our job is to estimate the thickness of the hair. We need to find what t is equal to. So we can rearrange this equation for t. T is equal to L lambda over 2 delta x. Now, we said that this entire length of glass plate is equivalent to 9 bright and dark fringes. So we're going to replace L with 9 delta x. We have delta x on top and delta x on the bottom, so we can see that these will cancel out, and we are left with t is equal to 9 lambda over 2. If we know how many dark fringes are present between a given length of glass, then we can actually use that to calculate the thickness of the object causing this resulting interference effect in this air wedge. So we're going to do that. 9 times 6 times 10 to the power of negative 7 meters divided by 2. When you punch this in, you end up with 2.70 times 10 to the power of negative 6 meters, which is equivalent to 2.70 micrometers, if you care to convert it into micrometers. Therefore, the estimated thickness of the hair is 2.70 times 10 to the power of negative 6 meters, or 2.70 micrometers. So imagine this. Imagine you had two plates of glass and they were demonstrating an interference pattern caused by an air wedge. You would know that a small object is causing this wedge, and you could use the number of bright fringes that are present on that sheet of glass while viewed from above to determine the thickness of the object causing the obstruction. Actually, a very valuable tool that is used very often. Okay, I want you to try practice problems on page 507 and 510, as well as review questions on page 511. Good luck.